morning. Thank you for your presentation. First, I'd like to ask, what kind of collision we have between the magnet and the ball?
Collision?
Yes. When they have the collision.
Yes.
What kind is it?
I don't know what kind they...
elastic, inelastic,
well,
elastic.
there will be a little bit deforming, but I think that's electric.
The linear momentum conserves on the system. The linear momentum, mass times velocity.
Yes.
Yes, completely.
No, what's the question?
If the linear momentum is conserved in the system. It's quicker. I have
the linear momentum.
Okay.
Yes, I think so.
Yes. I don't agree, but let's talk about that later.
Okay.
The total energy of the system is conserved.
Yes.
Yes, there is no friction nor dissipation.
Well, there is, but all energy is always conserved.
What interactions are the most relevant in this problem?
The interactions, I think, between the steel, between the upcoming ball and the magnet.
Okay. What is the optimum case of spheres after the magnet? How many spheres exactly?
How many spheres?
Yes.
What do you mean?
After the magnet.
Yes.
How many spheres?
Well, there's a sphere of the magnet itself, but the magnet magnetizes the steel balls in between the magnet and the Gaussian.
After the magnet.
Hoeveel ballen liggen er tussen?
Oh.
The opponent of the Gaussian cannon, problem number 1. First, the theory. The theory consists in the definition of the Gaussian cannon and the gain of velocity of it. Then the experiment, he had a constant velocity and a video and a graph. In the conclusion, he wrote the number before and he measured the number before and after the positive points of the theory. He presented the system, the energetical analysis, the impulse, and the velocity gain. The negative points, he neglected dissipation. He didn't know how to answer about the collision. The optimal number of spheres after the magnet were not optimized clearly. The size of the ball were not measured, nor the size of the magnet, and we believe this is really important for the problem. The radio of the size of the spheres and the magnet, and the total elastic collision was not analyzed. In the experiment, we had the positive points, he controlled the launch velocity, and he had a good use of medium. In the negative points, he did not vary the number of balls after the magnet, the radial size of the balls and the magnet. He didn't vary the magnet nor its composition. The magnet is not fixed. This is not good for the analysis. He had no optimization of the parameters by the initial number of balls. The number after the magnet nor the magnet size. Thank you. And now we'll go to the discussion. First, I'd like to ask: does the total kinetic energy conserve?
Total kinetic, which you mean?
The kinetic energy.
Of the ball,
Before and after. The collision. No, okay. What is the relevance of the radio between the radius of the spheres and the radius of the magnet?
You mean the size of the balls of the magnet?
Yes.
Well, like I said, there will be loss of kinetic energy if the steel balls are small.
But is there any optimal point of the size of the magnet and the size of the spheres?
Yes, I think that the optimization is equal size.
equal size. And can you explain that? Why would this be? Why would this be the optimal size?
Actually, it depends on how you have set the what the setup is. Because what I did, they just lie on the same.
Do you
same
think
height.
the magnetic field lines change because of the sphere?
Yes.
Yes,
They
and
get magnetized.
how does it change? Are they attracted to the steel balls? Are they reflected? What happens?
If you have a magnet, and
Oh, please quicker here. We don't have much time.
well, the field magnets will be this. If you have here the north and the south,
Okay.
and if the ball comes near, you will get also magnetic field.
Okay. I
This
don't agree with that because I
What do you
think
think?
if you have the magnet here,
Yes.
first we have this kind of lines,
Yes.
and then when we have the steel ball, the lines will be attracted inside the material because it's energetically favorable. Because we have a higher permittivity of the ferromagnetic material, and then the energy of this field, this magnetic field, would be lowered. So it's energetically favorable for the magnetic field lines to be inside the ball.
And how you think that the steel ball is magnetized?
Yeah, we have induction of current that I also didn't talk about. And how does the optimization of numbers after the steel ball behaves if we change the magnet or if we change the radius of spheres?
If the magnet is stronger, you will need to have more spheres in between to even get the ball bouncing up. Because
Do you believe the friction is relevant with the ground?
yes.
And how does it influence in your final number of spheres, the optimal size? Do you think it interferes or not?
No, I don't think so, because they don't. These ball in between, they don't move. Only the bouncing one and upcoming ball.
Okay, I don't agree with that because we have a higher dissipation if we have a higher number of balls. That is, if
But it isn't moving.
the balls have an interaction to the magnet, right? The balls after the magnet. So if we have that, the optimal number would be infinite. And we do not see that because we have dissipation in the collisions.
Yeah.
So we have optimal number depending on the friction with the ground that you could have variated and depending on the number of balls.
But how do you get the friction if you don't move?
You have dissipation of the mechanical wave and you have dissipation with the ground as well because they are not completely still.
What is this?
Okay. Now for the hysteresis of the ball, is that relevant? Hysteresis.
What?
Hysteresis. Yes, we have
Write it down.
the magnetization as we have a graphic like this.
Excellent.
And if we apply current in a ferromagnetic material, it will still be magnetized after we stop applying this current. So we could have this influencing the behavior of the steel balls in this problem.
Okay.
You mean that the bouncing ball will still be a little bit magnetized?
Yes.
Yeah.
Would it have you try to minimize this effect so we could have better experimental data? If you use always the same ball,
So you will lose kinetic energy that way.
can you go back to your video that you showed? Because I don't think it's very accurate.
The left side, please. Lights. We have the lights on. Thank you.
In het begin.
Ja, ja.
Hij is...
Yes. So you can see that the center of mass is dislocated, right?
Yes.
Do you agree that it's not the optimum point, like this?
No, this is not the optimum point. That's why I said it. I made a mistake. I lost some kinetic energy.
Okay. Is there a dissipation of the mechanical wave? When the ball reverses the magnet, we have a mechanical wave that is transferred to the other way.
You mean that the balls are getting deformed